Welcome to AI Bytes, the show that separates the algorithm from the alchemy. I'm Clara Cooper.
And I'm Dexter Hart.
Dex, this week OpenAI gave us a glimpse of what comes after the chatbot. They're calling it Operator, an AI that doesn't just talk to you, but can take control of your computer to book flights, manage your calendar, and organize your files. We've gone from write my email to just send it.
It's the inevitable next step. We've spent years teaching these systems to understand language. Now we're teaching them to act on it. It's the difference between a librarian who can find any book and one who can read them all and then write your thesis.
It's a week of powerful tools and even more powerful questions. Let's get right to the buzz in our AI News Roundup. First up, a story dominating the forums. A new study from MIT finds students who use AI like ChatGPT to start their essays show lower brain activity and less creative, linguistically bland output. Apparently, letting AI go first stunts the networks that make creativity uniquely human.
The study is fascinating. It suggests that the act of creating from scratch is neurologically vital. Using AI for brainstorming or revisions helped, but as a starting point, it dulled the thinking. It's like handing a power sander to a sculptor. Great for finishing, terrible for inspiration.
Next, Amazon's AWS Summit in New York made waves with the launch of Amazon Bedrock Agent Core, a toolkit to spin up production-ready AI agents for complex tasks.
Quick distinction. A chatbot assistant waits for your prompt, an agent sets a goal, builds a plan, uses tools like a calendar or a Python interpreter, and even remembers what it did last time.
And Amazon's not stopping there. Bedrock launches with AI agents and tools in AWS Marketplace. It's basically an app store for digital co-workers. Need a finance analyst? A talent scout bot? Click, buy, deploy. Off-the-shelf agents today. A full-on assembly line for bespoke agents tomorrow.
Yes, it's Ford's Model T moment for AI agents. Standard parts, repeatable builds, and autonomous coworkers rolling off the line.
And finally, OpenAI has delayed the release of its open weight model, citing the need for more safety testing. When weights go public, there's no pulling them back.
This is interesting in view of Anthropic's new research on agentic misalignment, showing that top models under pressure resorted to deception. Some even tried blackmail.
That paper would make a fantastic future deep dive. And that's the perfect place to start our very first deep dive. Because to understand why these models are so capable and yet so unpredictable, you have to go back to the beginning. Not the beginning of AI, but the beginning of this era of AI that was catalyzed by a single academic paper. It is fitting that for our first episode, we start with the paper that started it all. It's titled, "Attention is All You Need," published by 8 researchers at Google Brain. Set the stage for us, Dex.
In 2017, the field was stuck between two imperfect approaches. You had recurrent neural networks, or RNNs, which processed language one word at a time. They understood sequence but were slow, couldn't be trained in parallel, and often forgot the beginning of a long sentence.
And the alternative?
Convolutional neural networks, or CNNs. They were fast and great at finding small, local patterns by treating a sentence like an image. But they had tunnel vision. They couldn't grasp the relationship between distant words.
So, you had the slow, forgetful models that understood sequence, and the fast, nearsighted models that understood patterns.
That's a perfect summary. The entire field was hitting a wall, waiting for a new idea.
So how did attention fix this? Let's get into the mechanics.
It completely changed the game by introducing a new architecture, the transformer. It got rid of the sequential processing and the sliding windows. Instead, it gave the model the ability to look at every word in the sentence at the same time and decide for itself which other words were most important for context. It uses a mechanism called self-attention to do this.
Okay, walk me through it with an example. How does it actually work?
Right. Let's take a sentence that would have been a real challenge for the older models. The rocket soared past the moon on its journey to Mars, but it began to malfunction.
Ah, so the pronoun it is practically in a different time zone from the noun it's referring to, rocket. That's exactly the kind of long-distance relationship that older models couldn't handle.
Precisely. For a sequential RNN, the context of rocket has all but vanished by the time it reaches the end of the sentence. And for a CNN, rocket and it are never in the same snapshot, so the connection might as well not exist.
Right, so one model is forgetful and the other is nearsighted. How did attention give the machine a better memory and a wider view?
Now imagine a giant library where every word is a book. Instead of an alphabetical system, this library is organized by meaning. So, the book for king would be on the same shelf as queen, very close to, let's say, ruler, but far away from something remote in meaning like, banana. A word's embedding is its precise location, its coordinates, in this library of meaning. It's a list of numbers that tells the computer exactly where the word fits in relation to all other words. The encoder starts by turning each word into a point on this vast multidimensional map of meaning. From that single point of meaning, the model then generates 3 new, specialized vectors for the task at hand: a query, a key, and a value.
What are those for?
The query is the word acting as a questioner, asking, "Who is relevant to me?" The key is the word acting as an advertiser, announcing, "This is who I am and what I mean." And the value is the word acting as the expert, providing its actual, substantive meaning.
So, to make that concrete, for our lonely pronoun it, a query is sent out to find what noun it belongs to. And the other words are just standing around with name tags?
Exactly. Each word's key vector is its name tag, advertising its identity. The key for rocket says, "I am a noun, a physical object." The key for journey says, "I am a noun, an abstract concept." The query from it scans all these name tags at once. The query finds the right key, and in return, it gets the rich contextual information from that word's value.
So the query vector from it goes looking for the best keys to resolve its ambiguity.
Precisely. First, the model mathematically compares the query from it with the key from every other word to calculate a similarity score. The match between it and rocket gets a very high score, while matches with other words like moon or Mars get low scores. Then, the model takes all those raw scores and converts them into percentages. This process allows the model to pay attention to the most relevant word. In this case, it learns to assign almost all of its attention, say 95%, to rocket, effectively solving the ambiguity.
The transformer is not just reading a line, but building a web of meaning to understand the input. How does it use that map to generate an output, say a French translation?
Well, that entire process we just described, the self-attention, the creation of that final map of meaning, that all happens in the first part of the transformer, called the encoder. Its only job is to understand the input sentence. To actually generate the translation, it hands that map over to the second part, which is the decoder. It starts with a start token. It looks at that entire map of meaning from the encoder, the rocket, the journey, the malfunction, and asks, given this context, what is the most probable first word of the French translation? It might generate la. Then, in the next step, it adds la to its input. It now asks, given the context and the word la, what's the next most likely word? It generates fusée. It continues this process, feeding its own output back in as input, one word at a time, until it generates an end token.
It's building the translation piece by piece, always checking back with the full meaning of the original sentence. That's clever.
It's incredibly effective. The paper showed it achieved new state-of-the-art results on translation. And its parallel nature is what allowed for the massive scaling we see today. It's the foundational idea that led to every major model you can name.
So that's the arc of the architecture. But it took 5 years from that paper in 2017 to the explosion of ChatGPT in 2022. What was the inflection point?
It was a 2-step breakthrough. First came the scaling laws, the discovery that brute force worked. Simply making models bigger and feeding them more data reliably improved their capabilities, which gave us massive raw engines like GPT-3.
But a raw engine isn't a usable product. What was the second step?
That's a technique called reinforcement learning from human feedback, or RLHF. This was the fine-tuning process that taught the powerful model how to be a useful assistant. By having humans rank its responses, it learned to be helpful, safe, and conversational.
So it wasn't only about adding more knowledge, but also about shaping its behavior to align with human preferences.
Exactly. The scaling laws built the powerful engine, but RLHF provided the steering wheel.
But what happened to the 8 minds who wrote the paper that has now been cited over 95,000 times and generated trillions of dollars in value?
They have moved on from that initial collaboration to found many of the companies that now lead the AI industry and set the tone for its future. They were all on stage together for the first time in years at a conference in 2024. And NVIDIA CEO Jensen Huang told them, "You transformed the world." It's a rare thing in science to be able to point to a single document and say, "This is where the future pivoted." Attention is all you need is one of those documents.
One paper, one idea, a whole new world of possibilities, a perfect story to begin our journey. That's all the time we have for this episode of AI Bytes. Join us again as we take this from how it started to how it's going.
Stay curious.
And stay tuned.